something else here.
You just put that in your pocket or on your waistband.
I'm going to put it back here now. What did I used to do? Somebody's here I could look at. I actually had to put somebody sitting there so I could look at.
Yeah, I'd have to sit up there.
Huh?
I'd have to sit out there.
Yeah. Okay, thank you very much. فکر کردی پس من کجاییم؟ علی خان فکر کردی من کجاییم؟ Allah, چی دارم؟ Oh, I guess that when I go close to that, start screaming or something?
Yeah, you get too close.
Okay. Oh, is it 9 o'clock yet? Yeah, we'll start. Okay, thank you. Good. Oh boy. این کار ما یکم سرد شده. Good morning. Good morning, Ron, Richard, and Alex. Hello. All's good? It's 9 o'clock, so we'll start. My name is Bahram Zarin-Afsar. I'm an architect, licensed engineer. I'm president of ZarinAfsar Associates, Architects and Engineers in Urban Design. I am going to start with San Fernando. I'm going to be obviously talking about concrete, reinforced concrete. I'm going to start with San Fernando Earthquake. This is February 9th, 1971, about 6:41 a.m. And we had the Northridge Earthquake. I'm sorry, the San Fernando Earthquake. The center, epicenter is shown here. This is the perceived shaking versus moderate all the way to severe shaking. Potential damage is indicated here. Peak accelerations are stated there, and so forth. Just want to let you know, get a sense of what the this earthquake caused, and the color, it's color coded where it was violent and severe and so forth. This is one of the disasters that happened. This is the Olivia Hospital, reinforced concrete building. This is basically what happened to that structure. I want to, we're going to be going over the fundamental concrete design and so forth, but I want you to pay attention to what you can see here. The column and the collapse of the structure. Here's another view. Have you seen this before? No. I like to show some of this to really. I'd like you to be engineers, not accountants. You know, I want you to think about what you're doing. This was at the time up to code. And so forth. Here's additional photos of the structure. Take a look at the column. It's basically the rebars are sticking out, and the ties are basically destroyed. This is a poor engineer trying to see what happened, really. There's a collapsed portion of it. Thank God, apparently on this building, not too many people were there, too early. Then I'm going to jump into What should have happened? I mean, you should, in designing buildings, you have to have the stiffness of the a gradual stiffness in the structure, and not abrupt stiffnesses at floors. So this way, the building is more flexible, and loads do not get concentrated in one area or not. This is the Van Nuys building. Here's what happened to this 7-story building. All of a sudden, there's damage to the 5th floor columns, and not many to the other portion of the building. The reason for that is based on Professor Trifuni. He actually predicted this collapse on computer model, where you have abrupt stiffnesses, changes, those areas get hit. Again, more of Olivia Hospital. Now I'm going to turn into, good morning, Richard. I see you typed in. Good morning. Then I'm going to Northridge Earthquake. This is January 17, 1994. By the way, I was here when both earthquakes hit, both 71, 94. I was like 11 years old then. But the 94 earthquake, about 4 a.m. again. And this is the parking structure collapse. You could see, I'm showing some of this stuff is to, you're all going to be licensed and so forth, and shortly. To think beyond the code and be good engineers than just following the code, being accountants. But you know, you could see actually the concrete columns actually are ductile. They perform pretty well as far as ductility, but the structure collapsed. Here you can see the cracks. How ductile the frame was. Some brittle issues here. So the point of this few minutes is that I want you to question your work. And code is the ultimate thing. Code is minimum requirements. And question yourself, check your work, and see what's right to be done, not what everybody else does. Okay, now that preaching is over, we'll start with concrete, reinforced concrete. First, I'm going to start with the material. Reinforced concrete material, as you know, it's concrete and steel, and due to the fact that concrete is not good intention, we provide steel to compensate for that lack of material characteristic, and have a combination of two materials, concrete and steel, work together to create the beams and whatnot, structural elements that we basically use. I put this graph for comparison. This is concrete, this is stress over versus strain. Concrete about 3,000 to 4,000, maybe a little higher. We'll talk about that, but normally around this range. Steel 29,000 29,000 or 29 million psi or 29,000 ksi. And the strains that you could see, what steel possesses versus concrete. Now, this material, concrete, is a mixture of aggregate, cement, water, and contains some admixtures. We have a type of Portland cements that's used. Yeah.
Oh.
Yeah. No. Oh, yeah. Good. There we go. Okay. Good. So maybe I can go back here. The upper one. So in this one, so basically we'll be using, this is the concrete section, and if we bend this, there's tension at the bottom, so what we're going to do is put steel at the bottom of the concrete to be able to take the tension, and concrete is good in compression. This area would be in compression, and we're using both materials. Okay, I'm back here. The pen works. The type of Portland cement, we have type 1 Portland cement. Feel free to, if you want to take a photograph of what's on the screen. I have some handouts here that I've passed out. And if you're not here, you could maybe take a screenshot of some of the screens that I thought maybe you could use and so forth. Type 1 Portland cement is suitable for most concrete. Then there's type 2 Portland cement, has a lower heat of hydration than number 1 and is more sulfate resistant than number 1. It's commonly used in areas where the soil contains moderate amount of sulfate. But when it comes to moderate, I normally use type 5, but we'll talk about it. Type 3 Portland cement is high early strength cement. It's used for early strength if it's needed. I'll hold on here in case you need to take a screenshot and so forth. Feel free if you need to take a print. I mean, if you think it's useful, you can. If you don't think so, that's fine. Type 4, mainly used in mass concrete dams and other structures where the heat of hydration is dissipated slowly. Recently has been replaced by a combination of 1 and 2. Type 5 Portland cement is a sulfate-resistant type cement and is used in footings, basement walls, and elements that are exposed to soil containing sulfate. If there's moderate sulfate, use type 5 anyhow. So that's the material of the cement. Again, we are back to a strain stress diagram. We have lower strength concrete that you can see here. And then we could go to high strength concrete and so forth. The rupture strain of 0.003, we'll talk about how we use that. And modulus elasticity as noted here and also in your notebooks. Here's another stress strain curve for concrete that you could see for different type of concrete, 1,000 psi, 2,000, 3,000, and all the way to about 6 or 8. And you could see something really happening at this strain of 0.033, which would, based on experiments, I'll show you what has been decided. You've normally seen this strain compressive strength, the diagram where the design value has been chosen as that, 0.003, and these are the failures of columns and beams during testing. These are all reinforced members that were tested. Now, what I'm going to do is, you might want to take a picture of this one. So basically, I turned the graph around so you can really correlate with what's going on in comparison with this graph to the right. Here's the compressive strength, and then the strain. You can see a lot of failure happening after the design value of 0.003 strain. So that's why the 0.003 strain was chosen, because before that, most elements have performed well if they're reinforced. And after that, you see a lot of issues. Here's the tensile strength of concrete. It's shown approximately 0.013 to 0.08 of compressive strength. Pure tension is so-and-so. I'll go back to this, maybe I should, to this graph. Show you the concrete really fails in tension. It's not good in taking any tension. And we basically ignore it. Splitting, here's the range for splitting cylinder. This is a test they do, 6-inch by 12-inch